Today we will be talking about the second condition for equilibrium. So let's remember what equilibrium is. What is Newton's first law? If all the forces acting on an object in each direction add to zero, then the object will maintain its state of motion. If it's not moving, then the sum of the forces is equal to zero. It's going to stay not moving. Or if it's moving at a constant velocity, the sum of the forces would still be equal to zero. For example, if it's moving at a constant velocity and not accelerating. So if the forces acting on an object add to zero, then it will not start to move. Is that correct? The answer is wrong. So here we have net forces acting on this. They're equal magnitude pushed on each end of the object. The object won't move. But how about if we do that? What will happen? It will spin. If a rigid body is in equilibrium, then neither its linear motion nor its rotational motion will change. In other words, the acceleration of the x, the y, and the z are equal to zero. Then the sum of the forces in the x and the sum of the force in the y have to be equal to zero. And the angular acceleration is equal to zero. Then the sum of the torques have to be equal to zero. And this is basically the condition of equilibrium. We're adding more than just the sum of the forces as we did in the earlier chapters. Now we have to do the sum of the torques. So here it is formally. A rigid body in equilibrium has zero translational acceleration and zero angular acceleration. It's in equilibrium. Therefore, the sum of the forces have to equal zero, and the sum of the net external torques have to equal to zero. So we have the sum of the force of the x, sum of the force of the y, and z, and the sum of the torques have to equal zero. Okay, let's look at some reasoning strategies to solve problems like this. Select an object to which the equations for equilibrium are to be applied. Choose a convenient set of coordinates for the x and y axes and resolve all forces into these components. Draw a free body diagram that shows all the external forces acting on the object. And apply the equations that specify the balance of the forces at equilibrium. In other words, sum of the forces the x and the y have to equal zero. Then select a convenient axis of rotation and sum all the torques about this axis, and they must also equal to zero. And then you're going to solve any equations for any of the unknowns. So let's try an example. Here we got a lady at the end of a diving board. The diving board has negligible mass. The fulcrum is pushing up on it, and the bolt is pushing down. We know that because if she's pushing down this end of the board, this end of the board wants to go up, so the bolt must be pushing down. And the fulcrum obviously is pushing up. What we want to know is we want to find the force on the bolt and the force on the fulcrum. So we're going to pick a convenient coordinate system, which is up and to the right is positive. We're going to draw our FBD. Here we have the force of the bolt pushing down and the force of the fulcrum pushing up and the weight of the lady acting on this side. And we know the lever arms in which they act. Now we're going to sum the forces in the x and the y. In this case there is no x's, but in some cases you will have to sum the forces of the x as well. And we're going to choose up as being positive. Therefore we have F1 acting down, F2 acting up, and weight acting down. And unfortunately all we have is the weight, so we don't have F1 and F2. So basically that's as far as we can go with this one equation. So now I'm going to have to use the torque equation. So we're going to select a convenient axis of rotation and set the sum of the torques about this axis equal to zero. You want to pick a point that eliminates one of the unknowns. So if we pick this point here, it will eliminate this force, which we don't know. Then we'd only have one unknown. We could also pick this point here. It would eliminate an unknown F2, and we could solve for F1. It would be really silly to pick this point as an axis of rotation because it would eliminate weight, and that's the only one we actually know. So I'm going to pick this is the axis, therefore F1 will drop out. And remember that clockwise is negative and counterclockwise is positive. So I obtain this equation. Sum of the torques have to equal 0. So I have F2 times L2. So here is F2 times this length. And that will be positive because it's going to make it go counterclockwise. And then the weight times this length. And that will make it go clockwise. So that's negative. So now I'm going to solve for F2. I put the numbers in and I obtain this number. So that's how much F2 has to push up with. So now once I know F2, I already know the weight. I can go back to my original equation and solve for F1. And it comes out to be 950 newtons. Okay, let's try another example. Okay, an arm is horizontal and weighs 31 newtons. So the weight of the arm acting through the center of mass of the arm acts straight down at 31 newtons. The muscle can supply a force of 1840 newtons at this angle of 13 degrees. What is the weight of the heaviest dumbbell he can hold? So we don't know this weight acting down. We know all the lengths, but we don't know this weight. So the first thing we're going to do is pick a convenient coordinate system and make an FBD. So I picked up and to the right as being positive. I took this force and I broke it into components because I know that the solder joint has to push up and it has to push over. I know the weight acts straight down and the weight of the dumbbell acts straight down. And this is the muscle pulling up into the left. So we're going to select a convenient axis of rotation. I'm going to pick one that is going to eliminate some of the unknowns. So what I did is I picked this point here, and I did the sum of the torques around that point. So I have the weight of the arm acting out this distance, and that is negative because it's going clockwise. The weight of the dumbbell, once again, is negative because it's making it go clockwise. And the muscle is pulling it counterclockwise, so that's positive. And the lever arm is this distance here. Okay? Take a moment to see if you understand why the lever arm is this distance. Right? Since the shoulder joint was chosen as the axis of rotation, both SX and SY dropped out. If we had chosen another point, such as the center of mass of the arm, only this one would have dropped out. And we would have had to, we could have still solved the problem. We would have made it much more difficult because then we would have had to solve for S of X, S of Y, and the weight of the dumbbell. So it's really important to point out that by picking the correct axis of rotation, you can really simplify the problem. So we went from, if we would have picked this as the axis of rotation, it still would have worked, but we would have had 3 equations. By picking this equation, this is the point of rotation, we only have 1 equation. And let's go back and finish the problem now. So now that we have our equation, we can solve for the weight of the dumbbell. And it comes out to be 86.1 newtons.